Bohr's notion of an atom with these stationary states. And I think I intimated last time, right, that they actually figured out that de Broglie wavelengths, if you stretch them around the atom in some way, and here they're just trying to draw a picture of what it might look like. Notice that they didn't draw a picture of the fundamental over there, because what does that look like? I don't know. Right? It's like it goes in and out or something like that, right? But de Broglie brought up this idea that electrons could act like particles, and of course now we know they do. We can put them in electron microscopes, make pictures of them. We can make them diffract, right, and make overlapping patterns, and we're going to look at that in just a sec here. And so we know that they can act like a wave, and it all fits pretty well, right? There are certain allowable levels, right? In the same way that there are certain frequencies that we can make. If you play a trumpet and you blow into the trumpet, you get one note, and then if you blow a little harder, you get another note, and you never get the note in between. You can't play some note in between unless you're like really, really good and playing really high or something like that, right? Okay, so this works just perfectly, and this is the derivation, right? So these things, these wavelengths here, are basically the way this formula works is that your wavelength is twice the length over n. So if a fundamental is 1, the wavelength here is twice the length of that, and of course that's what it is. Yeah.
So those are the orbitals to your right?
Yeah. This is allegedly what they might look like, right? You know, but they don't really. They're like these bizarre shapes, and because it's three-dimensional and all this stuff, right? So you can derive that little electron in a box formula. I'll partition off this little chunk here, right? Okay. We start off with our kinetic energy, right? Is momentum squared divided by twice the mass. And that's true because we know it's 1 FmV squared, so this would be m squared v squared divided by 2m is 1 FmV squared, yes? All right, so sometimes we write kinetic energy that way. It's in your data packet that way. And then momentum isn't that, wouldn't that be h squared over lambda squared over 2m? I'm just substituting p as h over lambda, right? And then obviously we can make this a lot messier, right? Ek is h squared over, and then lambda is 2 squared L squared over n squared, right, times 2m. It's not going to get pretty. Can't we put the n squared up there? So n squared h squared, right? And then you have 2 squared times 2 is 8, right? L squared m, and you end up with that. So this is the electron in a box. That is, if electrons have acted like matter waves, this is the kinetic energy of those electrons as they do their thing, right? This is totally, it's in the IB packet. I'm just showing you where they get it, right? Presumably they could give you a problem where you have to calculate the kinetic energy of these things, but yeah, there it is. And you could try that. I gotta move on. Okay. So this is an interesting thing. Schrodinger actually solves a wave equation for the hydrogen atom, right? Heisenberg later actually solved it for helium, right? But nobody knew what it meant. What does this mean? How does matter act like a wave, right? This is a bizarre thing, right? But it really worked really well, because before that they were actually doing like calculus with matrices. If you can imagine two things, right? Calculus and matrices together. But they had this matrix calculus way of doing it. Schrodinger's way was much more efficient, right? The math was much easier to understand. But nobody understood what it meant for electrons to be a wave, right? What does that actually mean? And you're not going to like the generally agreed upon explanation any better, but that's it, right? So today is sort of the ghost stories. It's like, right? And we could only solve basically the Schrodinger wave equation for hydrogen. If we had singly ionized helium, then we could also solve it, because singly ionized, doesn't that mean you've got basically an alpha particle, 2 protons, 2 neutrons, but 1 electron? Yeah? That can be solved. 2 electrons, that's too many things moving, right? So this is terribly difficult, right? But this is what it ends up looking for. If you look at these wave equations, is that they're very dense there and they're not so dense there, right? And the ultimate interpretation of this, by the way, is that the wave equation corresponds to a probability. So it's not where the electron is, it's where it's likely to be. Yes? Okay. And by the way, this is some of the best physics we've got. Our predictions of the probability of electrons to be in a particular situation are some of the best agreements between theory and experimental data that we've ever gotten. But notice that we've let go of something. Notice that we've let go of like some sort of certainty sort of thing. Didn't we last year, like we solved for the orbit of a planet, and the planet moved at a particular velocity, lockstep, right? Yeah? It was deterministic. There it is. The Earth goes around the sun at a particular velocity, and you know, I've got software where I can go like 1,000 years in the future and predict the positions of the planets. Yeah? And it's going to be pretty accurate, right? We've got this is a good thing, right? This lets go of that. There's no sense that we're going to know when it's going to be there. And then more troubling for people like Einstein was that we're letting go of causality. We don't know what's causing this. There's no cause. It's just this quantum, pure quantum randomness, right? And there is, by the way, in the years since then, we have not come up with a theory. In fact, people have shown that there's actually is no hidden variable theory. It's not that we can't predict it because we don't know. It's because it can't be known. That's the nature of this. That's pretty strange. Isn't that strange? Yeah. So we can talk about the probability, right? But there's certain things that just can't be known. This is like women, too. Women are this way. I'm kidding. I'm joking. The heart of a woman just can't be known. You can talk about probability, right? I'm just kidding. I'm joking. And it's not a funny joke. Okay. You guys are thinking the hearts of men can't be known either, you know. It's like, I know. The brain of men can't be known. Anyway. So these are some pictures. If you do this, solve the Schrodinger wave equation, you get these crazy distributions, and they don't really make much sense, and they involve imaginary numbers. And I could solve all these little things. It was just a bunch of algebra, and really deeply didn't understand what it meant. Okay. So Bohr's model works really well. It worked for hydrogen, didn't even work for helium. Didn't explain the fine structure of the atom, but the Schrodinger wave equation, or the brightness of the lines. Schrodinger wave equation actually just solved why the lines were particular brightnesses. But there is a fine structure. If you put the atom in a magnetic field, you get the lines split into two. And did you guys talk about spin up, spin down in chemistry? Like electrons have spin, yes. Right? This is one of the quantum numbers, and this is pre that quantum number, right? So all you have to do is add that number, and you've really got the Bohr model, right? Didn't explain molecular bonds, and the idea is not that Bohr's theory is not correct. It's just not the whole picture, right? His theory is not totally complete, right? But otherwise, it generally took us. So there's Niels. I think we're supposed to clap. Right? Now we have to go to the Hindenburg uncertainty principle. I'm sorry, the Heisenberg. I always used to call it the Hindenburg.